Okay, welcome to this short workshop on Rayshader. My name's Sam and I'm a digital fellow with Graduate Center Digital Initiatives, and this video is for if you took part in the workshop last Friday, or if you're generally interested in Rayshader and want to see what an introductory session of it might look like. This workshop does assume that you have an introductory level of knowledge of R. If you don't, there's plenty of resources online for you to get there. This is not going to be a hugely demanding session, but you do need to know about how to enter instructions and commands into RStudio, so best to start there. Of course, I'm going to start here with an empty script, and one of the first thing that we almost always do within our session is turn on the necessary packages, or attach the necessary packages we have to our environment. So here I'm just going to install and attach DevTools or developer tools and tidyverse. I should say this is attaching, not installing. Installing is a separate process. We also need to install, for those that haven't done this before, to install and attach the RGL and Rayshader packages. Also, if you're using a Mac, you also need to install a small piece of open source software called Xquartz, and have that open. So bear that in mind. It's just a small piece of software that opens up a graphics window on your computer. It's in there on a Windows computer, but not on a Mac. So just make sure you have that installed. And for everybody, you want to install Rayshader from the GitHub repository. And the reason for that is that on the CRAN repository, the version of Rayshader hosted is out of date. It's an old version that has a bug in it, and the most recent version of Rayshader, as of the new year in 2023, is the one that is available on Tyler Morgan Wall's GitHub. So Tyler Morgan Wall was the guy that created this package. Rayshader. So we type in here the username and then the name of the package. Now, I'm not going to do this because I already have the packages installed. My recommendation is actually that you install RGL first if you don't already have it. Hopefully you won't find that these packages conflict with anything else that you already have installed and attached in your own session of R, your own computer, but you may have to play around and uninstall or deattach various packages to make sure that these work fine. This is a very small package that helps with opening graphics windows, and this is the larger package that should take about a couple of minutes, between 2 and 5 minutes, to download and install. One important thing that you should bear in mind about Rayshader is when prompted whether to install updates, just press enter in the console to skip updates. Don't press 1 or anything else. And this means that you install the right version without anything from the CRAN repository. Okay, so at this stage I'm going to assume that you've installed this, though you should pause the video or take the time that you need to install and attach the Rayshader package. When it's downloaded and available for you, you'll see in the packages window here on the bottom right that they break into 3 separate ones. You've got here Ray Image, Ray Render, and Rayshader. I'm just going to click these boxes, but of course, as you probably know, you can type out the command as well, just like, not like that, like this. Rayshader, Ray Image, Ray Render, and also the RGL package. So, the first stage of this workshop, now that we have the package available, is to create a file that's temporarily going to hold our downloaded data. So we'll create a file for our data. So I'm going to call it my data, and that will be the temp file. You can see it's come up there in the global environment. For some of you, this may be very simple. For those of you, some of you, this will be the first time you're looking at this, but that's okay. We'll go through it just stage by stage this way. The next step is to download our raster image. My data that we've just created is the destination file. So I'm going to use here a command called download file in the base R, and it's going to be at this URL, which I'm going to paste here rather than type out here, just to make sure I've got it right. It's Tyler Morgan Wall's personal website, and it's a zipped TIFF. It's a raster file that's been zipped up, and the destination is my data. So let's see how that goes. It looks okay. It looks like it's been downloaded. And in there, we now should have the data that we need. So the next step is to use the raster package to unzip and load the raster image. For those of you that are familiar with using read.csv, this is like using the function read.csv or anything similar like that, which is telling R to open up the data in the way that it knows how. So it's local TIFF, that's what we're going to call our file here. I'm going to use the raster package, the raster function, and we're going to unzip first the file my data into dem01.tif. And there we can see in our environment here on the top right, we have our data. We have our raster file. R seems to recognize what it is, and we're ready to work with this now. At this stage, as you have an optional step here, which is to delete the original files that we have attached. And this just means we unlink my data, the original temporary file. And you can, if you like, of course, you can also remove it entirely. Be aware, of course, that now that's been deleted, our temporary file, we can't get that back. That's been deleted permanently now. Now we have our raster data, and just for interest, you can see that we can actually plot the raster image in a basic plot. So if we just do this, and we put here local TIFF, we can see that the plots that has come up here, we get our first indication of what the file actually looks like. We get a sense of elevation, we get a sense of extent with X and Y coordinates, and we can get an overview really of what we should expect to see once we start modeling it in 3D. R has already taken a look at the data and made its color distributions relevant to the height, to the variations in the data that it sees. So let's go ahead with one of our first functions from the Rayshader package, which is to create a matrix from the raster image using Rayshader. For our case, LMAT means elevation data into matrix. Oops, elevation into matrix. And so we'll take the LMAT, that's what we're going to call it, and we'll use the function raster to matrix, and into this function we will put our local TIFF that we've just been working with. So what's going on here is we're going to create a matrix called LMAT out of the TIFF file that we have. It's going to be turning a raster image into a series of rows and columns. And here we have now, very quickly in our case, we have the matrix set up. We can open it in a separate tab. And here we have the full array of data, which is really quite something. And if you're working with larger files, this file in particular will be a lot larger and may take a lot longer to process. So be aware of that. The file we're working with is quite small today. It's the demo file, but it can get a lot more complicated as you use much bigger files. So be careful what you put into the working environment here. Okay, so for those of you who are interested, of course, we can also just preview the data. Sometimes this is of interest just to make sure we have the right material in our environment. You can take a look at the head, the tail, and take a look here in the console at the data we have available. It's not telling us a great deal right now, but it's good to know that perhaps the data is in the right range. So we'll do our first shading instruction right now, which will give us the first insight into what Rayshader can do with the data made available to it. So the sphere shade function maps a color texture onto a surface by spherical mapping. And our available textures, I'll paste here. Rayshader comes with a series of available textures, IMHOF 1 through 4, along with desert, black, white, and of course unicorn, which is a bunch of crazy colors. You can make your own custom textures. I won't go through that today, but know that it is an option. So the process here, which will be repeated a couple of times now for the rest of the workshop, is we take the elevation matrix, add a pipe, and then we do sphere shade. As you can see, R knows it's a function from the Rayshader package. Inside the brackets, we're going to put here texture, and we today will choose the desert function. The final part of this now is to plot the map here. So it's 3 lines of functions, and there we go in the bottom right. We have a nice rendering, a first start rendering of what this looks like. You can get a sense. There is similarities between the image that you see here in the first plot and the second one now that we're starting to shade in the elevation. Okay, now one important thing to know here is that with the sphere shading, this is a graphics rendering process that shines. It records how light reflects off a surface inside a sphere of infinite size. It's an old rendering technique that was often used for computer games, and what you can do is shift. It has one light source, and you can shift the light source or sun direction using sun angle. So I'm going to copy our previous lines of code here, and inside the brackets I'm going to put sun angle equals 45. What you want to do is put a value between 1 and 360, i.e. 360 degrees. And you'll see now, if I execute this, you'll see how the light changes on the plot. It's almost like an opposite direction now. And this is, largely, for like many other functions in this package, it's largely aesthetic, but you can also make it technical if you're working with times of day and times of year and stuff like that. So let's move right on to the add water function. Add water function, which adds a water layer to the map. You can use standard textures, a hex code, or a color string. And we're going to add a new line to our existing code. This time it's add water. And inside the brackets, what we put here is a new function called detect water. And we detect water from the elevation matrix and make sure the color is going to be the same as the rest of our map, desert. Now, the way this works is you add the water to the map by using the function which determines flat regions on the map. So you can change the parameters, but what happens is this add water function seeks out parts of the matrix where the changes in value are essentially nil. And so if you look at the map here on the right, there's this flat region where the elevation doesn't seem to change at all, and that's because it's ready to be rendered as water. So this is how it ends up looking. We have a nice river here. It identifies that there's no change in elevation in these regions and so it colors it with water. Now, of course, you don't have to stick with this. You can do something like that. You could add basic colors and we get a nice red river like that. You can experiment with all kinds of different color palettes, but we'll stick with the regular theme for this session. Okay, so now we'll use one of the perhaps more computationally demanding functions here. We're going to add a ray traced layer from that sun direction as well. Ray tracing simulates a variety of optical effects. Such as reflection, refraction, soft shadows, etc. And I'll add one more comment in just a minute, but let's get ahead with doing this ray tracing and we'll see what the effect is like. The new function to do ray tracing is not add water, but add shadow. And so we add shadow inside this function. We put here ray shade. We tell that the data source is going to be the elevation matrix as normal, and we also have to put a variable number in there as well. So this number, I'll add this comment now. The variable seems to suggest intensity of light and quality of material. I'm not familiar enough with the physics and the mathematics of how this works, but for now you can think about this variable as adjusting the intensity of the light, and I'll show you what I mean now. Just give it a text sector ray shade, and now you can see it's add an extra layer of shadows. If we go down to 0.1, you can see that it's much darker. It starts to look a bit like a PS2 game or something. And then if we go all the way up to, say, 2, it's extremely bright. And so that kind of change in intensity, almost like the contrast on a TV, gives us varying degrees of light intensity, and you can render it accordingly. But I'll leave it at 0.5 for the moment. And that is, for the moment, as far as we're going to go in terms of ray tracing. We're going to, well, in fact, no, we're going to add one more, apologies, we're going to add one more layer, and we're going, here it's going to be, we're going to add what's called an ambient occlusion shadow layer, which models lighting from atmospheric scattering. Again, we're going to have another numeric variable for the ambient shade, which darkens areas that have less scattered light from the atmosphere. This results in valleys being darker than flat areas and ridges. And so let's take a look at how that would play out. We'll take our original lines of code, and then we're going to add one more add shadow. And this time we type in ambient shade. Again, our data source is always going to be elevation matrix. And we'll stick with the same variable just for the moment. And let's see finally how this looks. Takes a while to process. And there we go. And now we really start to see how realistic this rendering can look once we add additional layers of shadowing. Again, we can go up and down in various ways to change the visual effects. It makes it a little darker. I'm going to return to our original variable, but of course you can experiment as you like. Now, we're going to do some 3D rendering, and an optional step here, just so that you know how to do this in the future if you ever need any troubleshooting. We're going to open an RGL window. This changed recently, so the new instruction is within the RGL package, we do open 3D. And all this does is, if we're lucky, it opens up a little window for us here. Nothing particularly special, there's nothing in it right now, but this little instruction just opens up a window for us. I'm going to close it again now, but know that if you need to open one of those windows, that is how you do it. So here, one of our final stages now is to use plot 3D to create a 3D model of the matrix and render it in a separate window. Again, we'll take almost all of our code this time. We're going to leave the plotting line behind. So we've got our pipe, and then the final line of instruction, I'm going to copy and paste it here from something I did earlier. It's a generic set of conditions or a set of configurations for this. But what's important to bear in mind is you start with the function plot 3D, then you use the data source, and then the rest of the variables here are to set up the view that you're going to see. So for example, here at the end we have the window size, the zoom, and a couple of other variables, right? But if you want to just keep it a very normal generic setup, you can copy these inputs here. So this will take maybe a couple of seconds, and let's execute and see what we get. And there we go. It takes a minute or so. This is not a particularly demanding model, so it doesn't take too long. But bear in mind that if you use bigger data sources, it is going to take you longer to get this generated. But you can click and drag to see different parts of the model. And of course, if you like, you can also zoom out and in. Be careful, because there's really no limit to how far you can zoom in and out. So if you have a dodgy mouse, then it's gonna need to be reloaded from time to time. So that's looking really nice. I'm going to put this window to one side over here, and we're going to quickly do a couple more things, just so that we know, just so that we can do some things with our newly found 3D model. One useful function is to turn the RGL window into an image in the plot window. And all you need to do here is type in render snapshot. We don't even need to put anything inside the brackets here. Whatever we have on our RGL window right now, we can choose a nice dramatic view. Just type in render snapshot here, execute the function, and what you get here in the plot is a nice JPEG of the current view in the RGL window. Very handy for if you want to export a nice quick image of what you've been doing. And for those of you who are interested in 3D modeling, here's an exciting function, which is to save the 3D model as a stereolithography file. It's saved in your working directory. So wherever you set your working directory for this project, that's where this project will this file will now go. So if I go to save _3D print here, and I'm going to call it almat.stl, give it the right extension, and I'll put here, you set the dimensions of the model, which doesn't matter too much necessarily. If you're planning to manipulate it in a different program, you can still do that. But for the moment, we can put 150, and that unit is going to be in millimeters. So 150 mil, square, 15 centimeters, nice and manageable size. So what this is you're saving your current model as a stereolithography file, which can be used in 3D modeling programs like Rhino and Rhino and SketchUp. And you can eventually print it in 3D if you want, using a 3D printer. So let's do that. And you'll see that it shows up in the directory that you're working. Let's see if we can find this. And here we are. And now it's being read not as a raster file, not as a matrix, but as a stereolithography file. And you can see it's come out really nicely, just as detailed as it's always been. And then you can go from there with other kinds of work. So that's it. And I'm going to leave you there. From here, you can add all kinds of other things, like scale bars, clouds. You can render depth of field, which is to say you can make some parts of the image blurry and some in focus. You can add population bars, and you can also add migration routes for animals or for journeys, for example, like a trek of some kind. And then finally, you can download GIFs of the model. You can do flyovers. And you can also render in high quality. So that's a suggestion of the kinds of things you can do afterwards, but we won't look at that now. That's something for you to look at individually. But really, there's an enormous amount of potential with this. And I hope this has been useful. This is by no means the full list of functions that you have available for Rayshader, but this is a good place to get started. And you can return to this as a reference if you need. And you can also contact me if you're having problems. Okay, thanks.